So let's pick back up where we left off in the last video. I got cut off there on the two types of covalent bonds. So, we were looking at our polar covalent bonds and we're looking at our non-polar covalent bonds. Well, the polar covalent bonds are going to be between a nonmetal and a nonmetal, and we said they're going to share their electrons unequally. And so I gave the analogy of like the North and the South Pole. You have atoms with different electronegativities, and when you subtract, and we're going to do some practice problems in just a little bit, when you subtract the electronegativities of the elements involved, you will get a difference. So anytime you see a delta X, that's the difference in electronegativity, which means you subtract. If you get a delta X, or an electronegativity difference between 0.5 and 1.6, that means you have a polar covalent bond, and we abbreviate that PC. So if you think about the analogy of the North and the South Pole again, if you have a polar covalent bond, then the electrons are being shared closer to one pole than they are another. Now remember, electronegativity is that pull on electrons that an atom has. So in this case, if these electrons are closer to the North Pole than the South Pole, that would mean that the North Pole would be the more electronegative element, and so therefore it would have more ownership than the South Pole. All right, again, think of electronegativity as a tug of war between the atoms as they try to share their electrons. So something like this happens between hydrogen and chlorine. Now, I will attach an electronegativity table in the module for you to print out, and you will need to use that to get your values. You do not have to memorize the electronegativity values. You will always be able to use that chart. So let's just do some examples of and classifying the type of bond as to whether it is ionic, polar covalent, or non-polar covalent. So I'm just going to use here. So just write this in your notes, write these examples, and I'm going to kind of open up a spot here. These are going to be our examples for guided practice. Please put these in with your notes. So let's do some examples. So for the first example I want to do, I'm going to consider a bond between boron and hydrogen. Now, you're going to want to refer to your electronegativity table. That's where I'm going to get these values from. But if you look on the electronegativity table, the electronegativity for boron is a 2.0. And for hydrogen, if you look at that, it's a 2.1. So we're going to try to find the electronegativity difference, or the delta X. That's what we're looking for here. And that's how we ultimately classify the type of bond. So you're going to subtract so that you get a positive number. So you're going to say 2.1 minus 2.0, and obviously you can do these in your head. Your difference is just 0.1. Now, if you go back to the notes where we've talked about the delta X ranges, basically, if you remember this, it's kind of easy. The two cutoff points are 0.4 and 1.6. I remember 4 times 4 is 16. So if your delta X is between 0 and 0.4, then you have a non-polar covalent bond. If the delta X is 0.5 to 1.6, which is what you have here, you have a polar covalent bond. So they're sharing, but just not evenly. And if you have a delta X 1.7 or higher, then it's an ionic bond, where the electrons have been completely removed from the metal and given to the non-metal. So here we have a delta X of 0.1, which means it falls in this range. So you would call this a non-polar covalent bond, NPC, non-polar covalent. Let's look at another example, example 2. So let's say we do a bond between rubidium and bromine. Now again, I'm getting these values from the electronegativity table that is posted in the module. You need to make sure you print that out. Rubidium from the periodic table, from the electronegativity table, Rubidium is a 0.8. So rubidium is a 0.8, and bromine is a more electronegative element. If you look at his value, he's a 2.8. So you always subtract so that you get a positive number. So you're going to say 2.8 minus 0.8. And of course, when you subtract that, you get a difference of 2.0. Now, look and see where that falls in the range. This is going to fall in the 1.7 or up range, so it's an ionic bond. You would say that's ionic. And let's look at a third example. So let's look at a bond between carbon and oxygen. From the electronegativity table, carbon's electronegativity is 2.5 and oxygen's electronegativity is 3.5. Again, let's subtract so that we get a positive number, 3.5 minus 2.5, and that's going to give me exactly 1.0. Look and see where it falls on the chart. It's going to fall in the mid-range here, so that's going to be a polar covalent bond. So remember, ionics are going to have a difference of 1.7 or higher. And in an ionic bond, the valence electrons are transferred from the metal to the nonmetal. There's no sharing of electrons. In a polar covalent, they are sharing, but unevenly. So somebody has more ownership of the electrons. And in the nonpolar covalent, they're sharing pretty evenly. They're pretty evenly paired up. One atom is not overpowering the other. So that's a nonpolar covalent. So the electrons are shared 50-50 right in the middle. In our next lesson, we will take a look at why chemical bonds occur in the first place.